Good morning and welcome. My name is Vladimir Bulovic. I'm the director of MIT.nano, this amazing facility right at the heart of MIT campus that you will have a chance to see later today. Welcome to launch.nano. Our goal today is to show you many different aspects that MIT.nano will support, as indeed we raise this facility from just the beginning of it to the future that's about to come. My honor for this morning is to introduce to you the visionary that indeed has propelled this from just the figment of our imagination to where it is today. President of MIT, Rafael Reif.
Well, good morning, and I would like to say welcome to the future. Look, in the company of so many experts in every branch of nanoscience and technology here this morning, I will not attempt to offer any news from the field, but I do want to reflect briefly on why we decided to create MIT.nano and why I'm so excited about its possibilities. Let me begin with some thank yous, well-deserved thank yous. First to Provost Mari Schmidt, VP for Research Maria Zuber, Executive VP and Treasurer Israel Ruiz, and to the hundreds of people across the Institute, from the faculty to facilities, who work so hard to make MIT.nano real. To all of them, I want to deeply thank you for your vision, energy, and particularly for your persistence. An enormous, heartfelt thank you also to the donors to MIT.nano for your encouragement and generosity, and for helping us make this day possible. Thank you also to the team that orchestrated today's terrific program, and to all of our outstanding speakers and panelists. And finally, on behalf of everyone who will use and benefit from MIT.nano for decades to come, I offer our profound gratitude to Vladimir Bulovic, who has devoted 7 years of his life to give life to this powerful idea. In April 2014, when we announced the plans for MIT.nano, we knew that putting a huge new building in the heart of campus would create massive inconvenience. Dust, noise, dump trucks, and detours for years. But we didn't hesitate because we knew it would also create massive opportunities. We began MIT.nano with a dream in 3 parts that would encourage and accelerate discovery and innovation here on campus, that it would create a catalytic new center of community, and that in doing all that, it would also serve to open a new portal to a rich scientific frontier. Today, I'm confident that we dreamers will not be disappointed. And to explain why, I will reflect briefly on each of these 3 parts of the dream. We were convinced from the start that MIT.nano would drive discovery and innovation on campus, where creating a world-class nano facility has long been a top priority for the schools of engineering and science. And the interest has grown rapidly over time across schools, across disciplines, and especially among faculty in the early phase of their research careers. What became clear, however, was that if we did it right, creating this facility would be much more than checking off an item on an academic wish list. Why? Because MIT moves forward like science itself. We make new ways of seeing, and then we see new ways of making. And we do make new ways of seeing, and we do see new ways of making. This simple, magnificent cycle from insight to invention describes the endless reciprocity between scientific discovery and technological advancement. That self-reinforcing cycle is the essential vision behind MIT.nano. And I believe it explains why there is no limit to the value of this facility in helping us to build a better world. Our vision for MIT.nano also included creating a new center of community. And looking around this room with this audience, I believe we have a head start on that part of the dream. Millie would be so happy if she could see this. I see faces here from every corner of MIT, and that is just as it should be, because MIT.nano belongs to all of us. Through its superb shared research and teaching facilities, MIT.nano will bring together many kinds of brilliant students, faculty, and research staff, scientists, inventors, and entrepreneurs, in spaces deliberately designed to trigger conversation, spark collaboration, and create community. In short, MIT.nano will help the whole institute continue to serve as a magnificent human machine for inventing the future. If MIT.nano only managed to give researchers and students excellent access to excellent tools and to each other's creativity, that would be pretty exciting. But I believe it has even greater potential. In 1945, MIT's former Dean of Engineering, Vannevar Bush, delivered a report to President Harry Truman. The report described the potential for federally funded scientific research to fuel invention and economic growth, provide new forms of energy, improve human health, and keep the nation safe. He called this report Science, the Endless Frontier. In the 7 decades since, science has advanced its understanding in every direction, including down to the nanoscale. But I'm certain that an endless frontier still awaits us over the nano horizon. I'm going to steal a phrase from a pioneer in polymer science and engineering, MIT professor Yanni Yanas. When young faculty ask him for advice on their careers, Yanni always says, go where the ignorance is maximum. Well, with MIT.nano, we're going there together as fast as we can. And I believe that what we will find there may give us the power to build, atom by atom, a whole new world. Let me close with one final observation. At MIT and across our society, there has been great recent focus on computing and machine intelligence and all things digital. That's understandable. In the coming decade, revolutions unfolding in the digital world, especially in artificial intelligence, will have profound impact on our society. But if we see the digital domain as the software of the future, it should be obvious that we need to invent the hardware of the future too. And that's where MIT.nano and all of you come in. On this milestone occasion I'm proud of and grateful to everyone who has brought us this far. I'm deeply optimistic about what you can all achieve together, and I offer you best wishes for a wonderful day of ideas. And now it's my honor to turn the floor over to a legendary member of the MIT community and a tremendous source of inspiration and support for MIT.nano, Mr. Ray Stata.
Good morning. I'm very pleased to be here today to help set the stage for the presentations that will take place about the many ways in which the MIT Nano Center and nanotechnology is shaping our lives. You know, I've had the privilege of serving on the MIT Corporation for many years, which was like having a window seat to the future. And from this perspective, I see today's launch of MIT.nano as another in a series of bold steps taken by MIT that enables our faculty and our students and our alumni to understand our world and to make it better. But this moment feels quite different, more pervasive to the campus and to the priorities of MIT because of just how fundamental and omnipresent nanoscale research has become. I don't think it's an exaggeration to say that the better world of tomorrow will be shaped atom by atom, molecule by molecule, by the researchers on this campus using the tools that MIT.nano will provide. The opening of MIT.nano resonates with me in a very personal way. I graduated from MIT in 1957. Just as I was graduating, two moments intersected to establish the trajectory of my life and my career, and set in motion the decades of discovery and innovation that transformed our ability to see and understand and manipulate the nanoscale. The first moment was the semiconductor revolution that became the cornerstone of Silicon Valley. It was in 1957 that MIT alumnus Robert Noyce, together with two other MIT graduates and 5 like-minded PhDs, co-founded Fairchild Semiconductor, a company that defined the beginnings of the semiconductor industry. In 1968, Noyce went on to co-found the Intel Corporation, which drove the fulfillment of Moore's Law and the spectacular advances that we've seen in semiconductor technology and in microprocessors. Noyce often was referred to as the mayor of Silicon Valley, and for good reason. By demonstrating the first integrated circuits, along with other pioneers like Jack Kilby at Texas Instruments, Noyce and his colleagues sparked decades of innovation in computing and communications that are the foundations of what has become known as the digital age. And by the way, I might mention that the founder of TI was also an alum of MIT, Cecil Green. The second moment occurred just after I graduated. In 1959, another MIT alum, the Nobel Prize winner, Richard Feynman, made a speech that foreshadowed the nano age. Feynman stated, if one day humans were able to master the ability to manipulate matter at an atomic scale, then we would be able to develop much, much denser computer circuits and remarkable microscopes that could see individual atoms. Well, Feynman was right, and over my lifetime, his vision has become a reality. The semiconductor industry that Bob Noyce launched required ever smaller transistor structures, driving us to learn how to use and implement the process of lithography, a method of shaping matter by defining shapes with light and electron beams. Today, through advances in lithography techniques, we can shape matter at a scale of a few nanometers, making features that are just 15 to 20 atoms across. To see the impossibly small features, just as Feynman had foreshadowed, we now can use remarkable microscopes to easily discern both the position of atoms and the way that they are bonded together. And just a few years ago, the most advanced microscopy techniques can even map three-dimensional structures of biological matter, like folded proteins, like DNA strands. And the understanding gained from these nanoscale images of biological structures can now accelerate our ability to discover new medicines. And by the way, in speaking of medicines and nanoscale, we should keep in mind that a molecule of aspirin is just 1 nanometer across. And so it is with most of the other drugs and vitamins that we consume. So it follows that if we are to understand how they function, we need to understand their operation at the nanoscale. So with the advent of recent advances in nanoscale instruments and techniques, we are clearly at the dawn of the nano innovation age, an age that was brought forward through the advancements of semiconductor technology and the digital age. I graduated from MIT just as the digital age was about to begin. I decided I wanted to start a company. If you had an aversion to authority, as I did, this looked like a very attractive career path. So after just a few years in industry, 2 partners, MIT alum, and I struck out on our own. We sold that first company to provide the seed funds for analog devices. So analog devices grew by making the best performing hand-assembled transistor operational amplifiers. So we were doing very well indeed, growing robustly, but the technology world around us was changing. The work of Robert Noyce gave us the direction to follow. So I surmised that we should shift the focus of analog devices to the business of integrated circuits. It was a bold but risky move for a very small company at that time, but I took the leap without knowing exactly where it would lead. That decision in 1969 to shift to the semiconductor business, designing and manufacturing analog integrated circuits, propelled the success of analog devices for many decades to follow. So you might notice as I'm sharing these stories with you today that the name MIT keeps appearing throughout the early days of the digital revolution. Back then, MIT trained people and their deeds moved the world forward, as they have done many times since, and as we're about to do again now. So I've seen firsthand the digital age unroll, and in light of that experience, I can tell you that in the upcoming nano age, MIT-trained people are bound to lead and significantly contribute, and the MIT.nano will help prepare them to do just that. So this brings us to today. For more than 6 years, I've watched the progress of MIT.nano's design and construction. And adding to Professor Reif's remarks, on behalf of all those present today, I'd like to recognize and commend Professor Vladimir Bolovic for his leadership in making this historic moment possible. Vladimir has dedicated a significant chunk of his life for the last 6 years and even before that to creating and fulfilling a vision for MIT.nano, a resource that will distinguish MIT for many decades to come. So thank you so much, Vladimir, for that contribution. So it's really thrilling to be here, to applaud the opening, as well as to join you in asking the question, well, what next? This morning feels like a characteristically MIT moment. Before we've even cut the ribbon on the most complex capital project in MIT's history, we're already looking ahead to the next challenge, or challenges, plural. To guide us over the course of today's program, we'll hear from MIT initiative leaders, faculty from numerous departments, industry partners, our colleagues from MIT Lincoln Labs, about some of the urgent problems that MIT.nano will help us to address: energy, health, quantum computing. And we'll also delve into the transformational role of nanoscience and nanotechnology in the field of materials, and then recognize the opportunity to design the world at all scales. So we are at the dawn of the nano age, and it's already shedding light on the secrets of the world of the very small, and illuminating the opportunities to build a better tomorrow. So I'm delighted, once again, to have a window seat on what promises to be a very exciting future. So it gives me great pleasure now to invite Professor Bob Armstrong, the director of the MIT Energy Initiative, who spearheads a campus-wide effort to advance game-changing energy technologies. Ask Bob to join me here at the stage and lead our first session on the future of energy built from the nanoscale up. Thank you.
Thank you very much, Ray. It's a pleasure to be here. And let me start by telling you a little bit about the MIT Energy Initiative, or MITI, as we call it at MIT, which is focused on addressing the world's grand energy challenge. That challenge I would describe as a twofold challenge. On the one hand, we need to meet rapidly growing energy demand around the world. That's driven primarily in developing countries by increasing population and by increasing standards of living, which go hand in hand with energy consumption. On the other hand, of course, we need to figure out how to create that energy system in a way that does not have or minimizes greenhouse gas emissions, what often gets put under the rubric of decarbonization. So that dual challenge is front and center in what we're doing. And of course, I think dealing with that energy challenge is a very appropriate task or goal for MIT, given our history of bringing MIT's multiple talents to bear on grand societal challenges. I think given our history of working well across disciplines, of working well across sectors, academia, industry, and government, we're well suited to this job. Susan Hockfield, who is president, who launched the MIT Energy Initiative a little more than a decade ago, had the vision to bring MIT's multiple talents together as necessary to make real headway on this problem. And I think that vision has been borne out as the right way to do this problem. We today, since, well, I guess over the last decade, since about 2008, when we had our first member meeting in the Energy Initiative, we've engaged a little more than 350 of MIT's 1,000 faculties, about 35% of the faculty. We have brought in to support that work about $700 million, a little bit more than that, funded by some 90 different industry and public partners on 5 continents around the world. We have supported about 1,000 research and analysis projects across the Institute, some 400 named energy fellows, thousands of graduate students and undergraduate students in their thesis research and UROP projects as ways to engage in this really important problem. As another measure of impact, since the Energy Initiative launched, MIT has spun out some 70 different startup companies related broadly to the energy area. Given how pervasive nanotechnology is in the energy field, we could have had any number of different faculty come here and tell you about the work that they're doing. I've asked 2 superstars in energy to talk to you in a few minutes. Professors Karen Gleason, a professor in chemical engineering, and Professor Yet-Ming Chiang, a professor in material science and engineering. Both of them have used manipulation of matter at the nanoscale in order to create innovations that have had significant impacts in the energy area. But before we hear from them, I have the great honor to introduce Professor John Deutch. He's had a very illustrious history at MIT as professor of chemistry, head of the chemistry department, dean of science, provost. He has been engaged in helping to create, to imagine and design and launch the Energy Initiative. He's also found time somewhere in his career to spend a lot of time in government, helping government in its significant activities. He was director of Central Intelligence. He was Deputy Secretary of Defense. He was Undersecretary of Defense for Acquisitions and Technology. And maybe more relevant to this discussion, he was in the small group of individuals who created the Department of Energy back in the 1970s, the latter half of the 1970s. So we've been really fortunate at MIT to be able to tap that broad understanding, that broad expertise, a way of penetrating through difficult problems with unique insight. MIT's benefited, MIT's benefited, and I personally have very much benefited from John's wisdom. So it's a pleasure to welcome John to the stage to give a talk.
Thank you very much, Bob. MIT.nano's new quarters are at a historic MIT address, Building 12, the former home of the Department of Chemical Engineering, which gave the tremendous advances in energy at the end of the Second World War and during the 1950s and 60s. Advances in petrochemicals, in polymers, plastics. All of this took place in energy at MIT in Building 12, the new home of MIT.nano. I came to Building 12 in 1959 to study chemical engineering, studied there with students such as Ken Smith, who became a professor of chemical engineering and the associate provost for research here at MIT, with Bill and David Koch, and especially with Sam Bodman, who remained my close friend for many decades, who passed away just 2 weeks ago and incidentally became Secretary of the Department of Energy. There were few, if any, women in the classes at chemical engineering at that time. The faculty at the Department of Chemical Engineering was of world class, and it did all those basic understanding that led to the Industrial Revolution of energy in the 1950s and 60s. There was Doc Lewis, Ed Gilliland, Tom Sherwood, Ray Bedour, but of course there were no women on the faculty at that time either. Happily, all of that has changed today. You will be hearing from Karen Gleason, Professor of Chemical Engineering, shortly. Today, Paula Hammond is the department head of chemical engineering, and I'm sure that Bob Armstrong joins me in saying that Paula Hammond is the best head of chemical engineering in 40 years. At that time, in Building 12, the tools of examination were unit operations, kinetics, mass and heat transport, distillation, all of them occurring on a length scale of 1 meter or more. I want to stress this morning the importance of length scale. Today, the scale of inquiry at MIT.nano is a factor of 10 to the minus 9th smaller. And we look forward to a future advance when we'll go down to the angstrom scale. But every time there has been a change in investigation at a different and finer length scale, there's been an improvement in understanding, an understanding about materials, both their function and their structure, and there has been an inevitable application made importantly, as Ray State has stressed, when we turn to microns and produce solid-state devices, an important practical consequence to that inquiry at a new scale. So it's not a question whether MIT.nano will make important advances. Not a question at all. It's certainly going to happen. It's not a question of if, it's a question of when these will happen and what they will be. What can be expected? It would be foolish of me to try and predict the advances that MIT.nano will accomplish. What will have the greatest impact on the field of energy going into the future? But there will be, I can promise you, exciting and important. Don't worry, they're going to happen. Perhaps they'll be in tailored surfaces, perhaps they'll be in catalysis, perhaps they will be in photoconversion or energy storage, but there will be important advances for energy. I want to next stress the need for integrating nanotechnology in its broadest context. And here I would like to quote a remark made elsewhere by Professor Karen Gleason, who has made the important observation that it's not enough to have an original idea, you have to make that idea work for the world. That means that MIT.nano, right from its beginning, must engage with other disciplines around it and see the largest presence of their technology in the society. They have to take into account the possibility, the necessity of economic, social, and regulatory issues if nanotechnology is going to have its impact in the future. Avoid the past mistakes of technology. All those great energy advances of the 50s were brought forward with an inattention to waste management from chemical operations or to the environmental effects. So it is important for MIT.nano to move forward, taking into account all the issues that make a technology successful for our country. Vladimir's leading role in the MIT Energy Initiative study of the future of solar energy sets the basis for him starting that process of opening the future of MIT.nano. I want to close with a remark about Vladimir Bulovich. To be successful, a university laboratory has to have an inspiring and capable leader. I know that many of you have reservations about Vladimir here in the audience today. I share those concerns. But it's not helpful at this inaugural day. It's not helpful to dwell on his limitations. Rather, I want to speak to you about Vladimir's strengths. Vladimir's greatest asset is how well he relates to people. People who have a wide range of interests, and he is always enthusiastic and open in dealing with them and their suggestions. This characteristic means that Vladimir will attract outstanding professors, outstanding students, and outstanding staff to this enterprise. Secondly, Vladimir is an exceptional scientist. He has done excellent work with a variety of collaborators across many fields that have had worldwide attention and sets what the standard is for what will be going on in MIT.nano. A third great characteristic of Vladimir is you can't tell whether he is from the School of Science or from the School of Engineering. You can't really quite identify his discipline because he's a person who focuses on problems, on the essential nature of technology, and how they should be addressed. This is the future of Building 12. I will always refer to it as Building 12, not as MIT.nano. And it's certainly not a characteristic of the past of the research that went on in Building 12. Another great characteristic of Vladimir is the clarity with which he presents his ideas, his plans, and his hopes for the future. This is more than a small advantage for establishing and growing a new technical laboratory that requires support from funders, from the technical community, and from the public. The layout and the concept of operations of MIT.nano is different than the traditional characteristic laboratories or centers at MIT, and it shows the way forward how MIT will be dealing with technology in the future. These talents assure that Vladimir is going to be a highly successful leader in this exciting new enterprise. He will have my support and my affection every step of the way. We are sure to see another great enterprise at MIT. Thank you very much.
Good morning. I wanted to take a little look at a change in the usual thing that sometimes less is more. In this case, I want to talk about that nano is more. And I wanted to give a picture, an image, to why it is you've been hearing all of these broad brush hopes for what we can do in the future. And in particular, I took this image. All the images you'll see today are from my own research, which a great part of it deals with sustainable energy. The first thing is that you're really seeing here on the nano scale, these bright areas are nano domains of between 1 and 6 nanometers in size, and they really help explain how this organic material conducts electricity. The interesting thing about this is it couldn't be taken here. It was actually taken at Brookhaven. And so with MIT.nano, what we really need is an increased capability. If we want to have innovation and discovery, we need new eyes. And it's a wonderful day that we're here to celebrate that those capabilities will be here. The other thing that's really unique is that the location in the center of campus, which I had a very front row seat as associate provost for 4 years while this was being, this ship in a bottle was being built, and everyone was being very patient with all of the disruptions it was causing in the main group, is that that location is so crucial for collaboration. And as you'll see in all of these examples, I have the references down the bottom, not that you can go look them up, but you can just see that there are multiple faculty in all of these efforts to solve complex problems, and they range across all of the schools of engineering and several of the departments in science as well. So, let's see here. So I don't know where the advance is here. Can someone help me? I could do nanotechnology, AV not so much. The green button. Thank you. All right. So Vladimir, in addition to all his nanotechnology, can do AV. So thank you very much. So here you can see a closer picture of that first one. And if you really look at the chemical structure, it's supposed to be a homogeneous material. You could have very simple chemical formula that would describe how the atoms are connected covalently in this structure. But what you see, because of the light areas are more ordered crystalline areas, this is really where the electrical conduction comes from. And so by being able to see this, we were really able to discover in detail how the conductivity changed. And it's really a quantum mechanical effect. We're looking at wave functions that describe those entire nano domains and how you have hopping conduction across the variable ranges that happen here. And by understanding this, you'll see at the end that we can actually make some advances in solar energy because we need conducting layers in those devices that are also transparent. And we really have now quantitative models that show, because we can see these nano domains, we can check our models and prove that we understand how this material behaves as a function of temperature. And what was really interesting is not only can we see that there's small crystalline domains, but we can see how they're oriented, and we can learn how to control that particular orientation. So the stack can lay directly across the interface underneath it, or it can be on edge. And we can see that through diffraction experiments and show that there are these distinctly two phases of matter. And so it turns out that that also affects the conductivity. So by changing the orientation over the years, we got one orientation that was called edge on that we would get routinely, but we learned how to flip it to face on. And as a result, the conductivity of the material changed. So it's now at a value of over 6,000 Siemens per centimeter, which is now in the range of what's typically used for a transparent conductor, which is the inorganic material indium tin oxide. The advantage that we have, and I'll show, is that our material is flexible while indium tin oxide is not. And that has several, that difference in mechanical properties has several implications. The other implication is that because it's organic, we can make it at low temperature. So if you make an inorganic material and you need a temperature of 400 degrees C, your paper or textile is not going to survive at that temperature. But we were actually able to show that this conducting organic material was able to be put on something as fragile as a piece of paper. And not only that, you could pattern it directly through a shadow mask. So you made the polymer, you have it as a thin film, and you have a pattern all in one step. And in fact, the capability to be able to do this, when I ran into Vladimir in the hallway over 5 years ago, he said, we can make some paper solar cells. And we did, and that was a very fun project. We can also do this on textiles, and through all kinds of torture tests on them, we wash them, we twist them, we stretch them, the conductivity remains the same. So now, instead of thinking about an age where devices need to be on silicon or some other semiconductor, we can have substrates that are very cheap, that everybody is familiar with, and that are highly mobile and lightweight, and that you can wear. While the materials that we make have this very small nanostructure, they actually can be produced on very large area. And this is something that chemical engineers do very well. We understand how to take something that's made at small scale, analyze that process, and then by modeling the velocities and chemical composition of the gas flows and the temperatures, we're able to do that now across very large area. So here you actually see a reactor that's at MIT that produces roll-to-roll of this conducting polymer. And here you can see the real advantage of the flexibility. If we were going to do silicon wafers, we of course can't do roll-to-roll because silicon isn't flexible. But if we do something like plastic or paper textiles, we can have this roll-to-roll manufacture, which is much cheaper because you can do much larger runs of material before you have to shut down the equipment. So the uptime is much larger. You also see here that the material that we make is indeed flexible by maintaining its properties. So the state-of-the-art material, the indium tin oxide, if you flex it, it gets cracks in it. And even after as few as 100 flexing cycles, the resistivity is a factor of 100 higher. What you see when you flex this conducting polymer is that you see no change in the resistivity. There are many ways in which nano can help us. We want to build these devices to generate energy and also to store energy, particularly for sustainable energy. We've been able to use the technology in my lab to define features down to the 7.5 nanometer scale, and to do so in multiple levels so that you can actually connect this very small features together. And we've also been able to take devices into the third dimension. And instead of building just on a planar surface where you have a limited amount of interface, you can add features to the surface so that that interfacial area increases. And it's at the interface that all the action happens. And we're still at an era where the characterization tools available for interfaces really are not sufficient to tell us everything we need to know. But we can systematically fabricate devices in which the aspect ratio of those features increases. And as you do so, you actually have to be more precise about the thicknesses of materials that you make, and you have to be on the nanoscale. To get the highest aspect ratio features, many people grow nanowires, and these actually are carbon nanotube nanowires, which we then coated with a polymer that was hydrophobic. And you can see here you have a 40 nanometer coating. And besides being useful for devices, that really changes the wettability of the surface. And back in 2003, we made one of the first ultra-hydrophobic surfaces where a drop of water sits only on the tips of these coated nanowires and has almost 180-degree angle of contact. We can use that same concept for making devices that store energy, some type of capacitor. And so you can take the nanotubes, shrink wrap them in this polymer, and the charges that you're storing are stored throughout the volume of the polymer. So the graph here, each of the different colors represents a different thickness of polymer. So we start at 0 in black for plain carbon nanotubes. And then if we add 3 nanometers of polymer and go to red, you can see that the charge storage has increased. So you have a dial that's actually on the nanometer scale. And we systematically changed it up to 10 nanometers and made very high capacity storage devices. And the precision of these layers is very high. And so here's another cross-sectional image of one of these polymeric layers. And this is actually on a spinel material that's useful for batteries. So you can see there the scale bar is 5 nanometers. So you're looking at sub-5 nanometer precision in deposition. And that's sort of a state-of-the-art for organic materials. And we expect that we'll be able to go further in the event of MIT.nano. We are no longer advancing, so I guess I will just wrap up here. I think in all cases, MIT.nano is really more, and it's more capability to see things for the future discoveries and keep hearing about all the people in the audience who are going to take MIT's name into the future. Thank you very much.
Good morning. I'm Yet-Ming Chiang from the Department of Materials Science and Engineering. And I'd like to tell you about something at a very massive scale. So I'm going to begin with a story. Aladdin says to the genie, I have just one wish. I would like free electricity, or if it's not free, at least no more than 1 or 2 cents a kilowatt hour. The genie says, I grant you your wish, but there's just one catch. You're going to get unlimited amounts of this electricity. And it's all going to come between the hours of 9 and 5 each day. So this is the problem. It's both an opportunity and a challenge that we face renewable energy today. And it's illustrated by behavior such as this. This is a plot of the renewable curtailment in California over the last 5 years. And what we mean by renewable curtailment is this is the generation capacity, mostly from solar PV, that we couldn't use and had to either simply stop generating or sell it at 0 or negative cost. Right? And you see that this is a plot month by month, and you see that it's increased systematically. And today, in a single month, we can curtail as much as 1/10 of a terawatt hour of electricity. That's a huge amount of electricity. Right? And this is at 30% penetration of renewables, and California has now, the California Assembly has approved the bill to reach 100% by the year 2045. So you can imagine how this problem will scale. Right? And not only will it be at massive scale, the duration over which we'll have to do something with this electricity will get longer and longer. Right? Here, the yellow curve is the solar generation. The red curve is the demand. And there's a mismatch here. And so ultimately, we'll need to take this under generation over the winter months and satisfy it with stored energy that we shift from the summer months to those winter months. Massive amounts of energy over monthly to seasonal time scales. Right? And so in order to get to this point, we can do two things with that excess electricity. One is to store it as electricity, which is a battery, and the other is to convert it to something else that we can store, such as a chemical fuel. And so I'm going to talk to you about the batteries today, right? And what can we do in the area of very large-scale energy storage. One thing that's going to be necessary is that the cost of this storage is going to have to be much, much less than what we do with, let's say, lithium-ion batteries today. This is an interesting plot. It's the last 60 years of battery chemistry development as we've pursued higher energy density for our cell phones, laptops, and our EVs. And you see that on a log scale, this slope is positive. And that tells us we've been doing something wrong. Our batteries are getting more and more expensive, rated by the amount we pay for the chemicals to store a single unit of electricity, a kilowatt hour of electricity. Right? And so for this large-scale grid storage problem, we have to take today's lithium-ion batteries and reduce their cost by a factor of about 100, right? And to where we reach a cost point which we have never seen before. Right? And the question is, can we do this? I'm highly optimistic that we can do this, but we'll have to take a different strategy than what we have done until now. For example, we'll have to look to materials and elements that are widely abundant, right, and at very low cost, of which sulfur is one of my favorites. Right? This is a stockpile of sulfur in Alberta, Canada, from refining the tar sands. It's 4 million cubic meters. Right? And so as a battery engineer, I look at this and think, how much storage is this? How many batteries could we make? And if we turned all of this sulfur into one type of sulfur-based battery, the lithium-sulfur battery, and used it to power electric vehicles, this would be 10 years' supply for North American and European light vehicles if every one of them had a battery the size of a Tesla Model 3. Right? If we turned it into a different type of battery for grid storage, which is where we take that sulfur, dissolve it in water, and run it through a device called the flow battery, this is a 4.5 terawatt-hour supply of stored energy. Right? The lithium-sulfur battery I referred to would also be 3 years of Google's electricity consumption. This 4.5 terawatt-hour would be an entire year. Right? And today, the way we store electricity, 95% of it, is as a technology called pumped hydroelectric storage. And this stockpile is 3 times the entire world storage capacity today. Right? So this is one idea, one approach towards a very low chemical cost of storage. Right? When we store at gigascale, the battery is going to look very different from what we know today. A EV battery today may have several thousand cells that look about like a D cell. Right? Instead, we're going to take our inspiration from technologies like pump storage. And what you see here in the middle, Ludington, Michigan has a lake upon a lake. Right? When there's excess electricity, you pump water uphill, and then you run it down through a set of turbines to generate electricity. Underground compressed air works in a similar way. We have a working fluid that's a very low-cost working fluid. It's water or it's air. The grid storage battery of the future, using chemicals such as sulfur, will follow a similar approach, but the working fluid will be a very low-cost chemical. Right? And we'll get energy densities that are 500 or 1,000 times higher than mechanical storage, which is what you see in the middle technologies today. Right? So on the way to grid storage, let's not forget about electric transportation. I don't know if we'll ever be able to create a battery with the energy density necessary for long-haul flight. But what I do believe is that within the next 10 years, we'll have, at least conceptually, energy densities that will enable the first step, which is regional flight or urban electric flight of the kind that Uber has envisioned. And in order to get to this kind of a future, you might ask at this point, what is it that MIT.nano will allow us to do? Right? So to store energy at these massive scales, we start at a nanoscale. And I want to give you one example here. Right? Today's batteries that are used in electric vehicles or for grid storage installations, such as you see in the lower left here, use materials which have a nanoscale behavior, which is very interesting. There's a compound called NCA. It has nickel, cobalt, and aluminum in it, which, if you have a Tesla electric vehicle, is the active cathode material storing lithium ions in your battery today. And it's produced in these microspheres that you see here, little ball bearings. Right? I have a little audio file of just 15 seconds I want to play for you. And if someone could turn that on for me. Whoops. There you go. It sounds like static. This is what you would hear if you put a sensitive microphone, we call it an acoustic emission sensor, on your lithium-ion battery as you charge or discharge it. Right? What's happening as that takes place? Well, you see it on the right here. We start with a pristine particle, and as we charge the battery, it starts to fracture. And then we cycle it fractures more. And if we go to higher voltage, where we get a lot more energy stored, it fractures even more. If you drive a Tesla or a Chevy Bolt, next time you step on the gas, think about this. Right? You can hear it. Right? And so what kinds of things can we do in MIT.nano? First is the characterization. We need to understand this nanoscopic failure, which comes from crystals distorting and expanding and contracting. These are breathing, living things. And then we can design chemistries that don't have this kind of built-in stress. Right? And that will allow us to take even a lithium-ion battery to the 20, 25, 30-year lifetimes that we need for grid storage. Okay? In closing, I want to say first, thank you to the tremendous MIT administration, and especially to Vladimir for his vision and the creation of MIT.nano. My office is in building 13, which is right next door to building 12. And the construction has stopped. The construction noise has subsided. Yeah. I can have conference calls in my office again. Yeah. So I, for one, believe that it's time to stop asking what we can do for MIT.nano, and to ask what can MIT.nano do for us. All right. Thank you.
All right, we will take a very short break, about 15 minutes. 9:55 we'll reconvene, and we'll start with a session on health and life sciences. See you shortly.